Good morning, mathematicians. How's everyone doing? Yeah, yeah. Oh, I need to go open up chat, and we'll get back to it. We'll get back to talking about crazy nonsense with D modules, sort of. Yeah. Or who knows, maybe people have questions for me today. I keep telling you guys to go prove things, and then tell me about what you proved. But it ain't popping off in chat like that. Yeah. Okay. So, we computed some characteristic varieties last time, and what was the point of this? These characteristic cycles of D modules, which we didn't give the full general definition, but I told you how to do it in the special case where you have a D module that's a quotient of a differential equation in this way. So what do we do? Sorry. What's the point of this? Okay, so to go back to some representation theory for a minute. So now we've seen a couple weeks ago, now I was talking about Langland's parameters. And one way to view these is as homomorphisms. So Langland's parameter for GLN is a homomorphism from the V group cross SL2C into GLNC, right? Subject to some other conditions, right? But we sort of talked about exactly how all the Langland's parameters for GLN get constructed. Basically, this part comes from Galois representations, and then this is a choice of something in some nilpotent element in the Lie algebra here. So then here's a mysterious process. For some reason, James Arthur, my mathematical grandfather, who's having his birthday conference in Toronto next week, writes down a second SL2 factor. Okay? He just does. And it works, and he calls these homomorphisms, well, he doesn't call them Arthur parameters, but now they're called Arthur parameters. And the point of Arthur parameters is basically, well, I guess there's a few things, but so every Arthur parameter gives rise to a Langland's parameter. So the Langland's parameter is defined by taking that Arthur parameter, is plug W and X in, and then in the second SL2 factor, you plug in this matrix, which is the norm of W 1/2, norm of W to the minus 1/2. Right, that's how you get the corresponding Langland's parameter. Okay, something's going on with chat because there's no way that nobody has said anything at this point. This long and straight. Oh, never mind. I was wrong. Okay. Hello, Arad. Normally someone says something at this point. Okay. Good to know. So Right. So Arthur parameters. Um, well, then there's also a notion of an Arthur packet. So we have a notion of an L packet, right? Those are all the representations that correspond to this. Oh, the delay's back. Well, who knows? Who knows? Well, this is unfortunately, I just don't think there's an easy way to explain it here. Well, the word parameter is just it's part of the name. So there's something called. It's not like there's a general term of something that's like, oh, this is what a parameter is, and then Langland's parameters and Arthur parameters are just different kinds of parameters. There's just the term Langland's parameter refers specifically to a special kind of homomorphism here between these groups that, well, if you go back, I mean, I don't know if you have the background, but hi, Jack. But if you do go back to some live streams from a couple of weeks ago, I talk a little bit more in detail about what Langland's parameters are and what they look like and examples of them. But it's if this means anything to you, it's a homomorphism of groups, basically. And so an Arthur parameter is also just another term. I don't know why we put the term parameter in there. Again, it's not like there's a general concept in mathematics of parameters, and these are subcases. In both instances, Langland's parameters and Arthur parameters are both just special kinds of group homomorphisms. But Arthur parameters give rise to Langland's parameters in this way. And, right, the Langland's correspondence predicts that there's a bijection between the irreducible representations of your p-adic group and corresponding, well, it's not just Langland's parameters. There's, well, one other way to say it is you get a representation. You get a representation of the complex dual group. Not quite of the complex dual group, but rather you look at the this group acts on the Langland's parameter by conjugation, right? So in the case of GLN, you can conjugate the image, and you look at the stabilizer, and then you look at the component group of the stabilizer. It turns out for GLN, these are always this is trivial. This is just the trivial group for GLN. So in that case, it does just become straight up Langland's parameters. We do need Kristap's parameters. Well, yeah, here's my proposal. put a third SL2 factor in. That's my proposal. Why? I have no idea. I don't think it does anything, but weirdly, for some reason, this does. But also, one thing we talked about is these parameters give rise to orbits in these Vogin varieties I talked about before, and the representations give rise to local systems on those orbits. So that's another way that one could phrase it, as a bijection between these things. So this means, for example, for GLN, all of the L packets are singletons, but that is not the case in general. So, anyways, if you have an Arthur parameter, the L packet associated to its Langland's parameter will be contained in the so-called Arthur packet. Now, what is an Arthur packet? This has a more complicated definition. Which actually I don't think I've fully internalized. Like I don't know how to compute examples of this in a fully spectral way, as we might say, in a fully representation theoretic way. But this is a theory. Like the definition of this was developed by Arthur, And one of the advantages to this is, so remember that we have like, we really want to study what are called automorphic representations. And so this is some kind of tensor product. This can be decomposed as some sort of tensor product over all of the, over representations of all of the p-adics, including the real numbers. And so we might want to know then, I mean, you might wonder, well, you know, we've got this full representation theory down here of like, I don't know, GLN Q2, let's say, let's look at this factor. And, you know, as we run over all what are called automorphic representations, which are the things that we really care about, whatever those are, as we run over all of those, do we hit all of these representations? And the answer is no. And the idea, part of what Arthur packets are supposed to capture, is that, well, it will show up. So if pi2 is an automorphic rep, then pi2 should show up in some Arthur packet. And that's part of the idea. Might be the place for this. It's definitely the place for whatever question you're about to ask. Just gotta make chat a bit wider. You're looking for a way to understand multiplication for the monoid monad. Anyone know anything about Levert theories? I don't, personally. The free monoid monad? Actually, Rod, if you have any suggestions on the... One of the students I'm tutoring was asking about... they found some random PDF talking about... which talks about natural transformations in Haskell, the programming language. And I just wondered if you had any good resources for talking about these things. I know once upon a time, a friend of mine explained to me how an array is a monad, but that has long since left my mind. And I'm wondering if there's a nice, precise, concise introduction out there that you know of. But I'll let the two of you keep going with your chat in the discussion, because I don't know so much about that. But there's a conjecture of Vogin, which conjecturally says there should be this other way. There should be this other totally geometric way. So it's called an Adams-Barbash, an ABV packet named after Adams, Barbash, and Vogin, who originally proposed this in the real group's case. And so the point is, this packet here has an entirely geometric definition. So I'll talk about what that is in a second. But then conjecturally, this should be the same as an Arthur packet. This should be the same thing as an Arthur packet. You feel like what Haskellers call category theory is quite different from what mathematicians mean. Yeah, the thing is, in this person's note, in the random PDF my student sent me, there was someone, they made some comment, the person who wrote the PDF made some comment about, I'm not sure this is exactly totally rigorous, or it doesn't, maybe this thing doesn't actually form a category. So, and then I was like, wow, Okay, that's why I was kind of wondering about other better resources on this notion, because I was like, well, okay, seems kind of wishy-washy. Could I talk about the Baum-Kahn conjecture? Maybe in a moment. I don't know much about it. Um, I'll have to pull it up, but in a moment. In a moment. Let me just finish this one train of thought here. So, um, the point is, yeah. And by the way, my mathematical sibling, Mishti Ray, who I've interviewed on this channel, by the way, in her PhD thesis, she proved this for GLN, p-adic GLN, that this is true, that these two things are equal, and is currently working on this for some other p-adic groups in collaboration with a bunch of other people. So, what's the point of the? Oh yeah, so geometric definition. So what does that mean? Well, so we have this bijection. So an irreducible representation can be associated to a pair of an orbit and a local system, and that in turn can be associated to a simple perverse sheaf. And the geometric definition basically looks at this. Well, and then also that simple perverse sheaf we know corresponds. Well, there's I guess different ways I could write this arrow. So there should be some D module as well that we can associate it to it, and then through the Riemann-Hilbert correspondence, also a perverse sheaf. So these are two different ways. And so one of the things that my supervisor with his collaborators proposed before was an alternative. So there was an initial geometric description given, but my supervisor and his collaborators found one that's arguably, well, that they found easier to do computations with, that's defined in terms of perverse sheaves. But the original one is defined in terms of D modules. So basically, if we let M pi, let's say, be the D module corresponding to this representation, then basically, I should say, this conjecture is true, but also the definition of ABV packets makes sense for general Langlands parameters. And so the conjecture, so one way to define this is basically in terms of the characteristic cycles. So I have to double check exactly when this is, but the condition has something to do with, I'd have to go back and review exactly what it is, and I need to, but the condition has roughly something to do with, so pi will be in the ABV packet. The ABV packet, it will be in the ABV packet when the D module, well, there's some way to look at the characteristic variety of the corresponding D module and its interaction with this orbit. So yeah, I'm drawing a blank on what the exact way is to formulate it. But so here's the whole point. Yesterday I talked about this computation here. And this is exactly essentially what this computation does, where I worked out what the characteristic varieties are, is it tells us what the corresponding ABV packets are. And so remember, maybe I'll write it up here. So we had sigma. Sigma 1 was this line, sigma 2 was the horizontal line, and then sigma 3 was basically the union of those two lines. And so the conclusion is, in that case, that we have, well, these two have the same Langlands parameter. And, well, in fact, there's only two Arthur parameters, and it's the two Langlands parameters basically come from Arthur parameters. And so what do the Arthur packets look like? Well, it's the representation, so pi 1, so that's the representation corresponding to like the D module of sigma 1, pi 1 and pi 3, and then the other Arthur packet looks like pi 2 and pi 3. So pi 3 sits in both of them, and that somehow has to do with the fact that like the characteristic variety for sigma 2 is contained in the characteristic variety for sigma 3. Well, the ABV packets aren't necessarily, I wouldn't say they're geometric shadows of L packets, but rather, let me show you. Okay, let me show you a picture. Okay, I'll talk about the Bohm-Kahn conjecture in a second, but let me show you a picture from a talk I gave. And I didn't. Yeah, I decided not to upload it because the audio quality was really bad. But maybe I'll do a re-recording of this talk sometime soon and put it up. But where is it here? So let me show you. There's some pretty pictures of. Let's get this out of the way. There's some pretty pictures in here of. So one of these is stolen from one of these pictures is stolen from my supervisor's one of his papers. So this is for the group G2, p-adic G2. And so this is one example. So for a particular choice of infinitesimal parameter, here's an example where we have 4 Langlands parameters: phi naught, phi 1, phi 2, and phi 3. And we can see these square boxes are their L packets. So we see 3 of them are singletons, and one of them has 3. It's kind of very unsymmetric. But then if you go over, you look on the right hand side, so now we see psi 1, psi 2, psi 3, and psi naught. These are the Arthur packets. And so now we see that this Arthur packet, psi 1, it contains, well, each Arthur packet actually contains 3 representations. So somehow it's like more symmetric now. And so the Arthur packets themselves are actually, in this case, psi 3, right, is just equal to phi 3. So in that case, that L packet is just straight up an ABV packet / Arthur packet. But in general, it's the Arthur packets will be like a weirder hodgepodge of L packets. So here's another example for a particular choice of family of Langlands parameters for SO7. So these are the Langlands parameter, or the L packets for SO7. And then here are the Arthur packets. So again, they're kind of weird combinations of these things. So the takeaway is something automorphic forms is a reason for us to care about computing the characteristic varieties of D modules. Now, let's look at the Bohm. I don't know how to say the names correctly. If these examples reflect general behavior, then you definitely expect the moduli space of Arthur parameters to be more well behaved than L packets. Yeah, I don't know. I don't know if there is any such thing. Actually, I was looking at the. Wow, what a happy looking picture. There's some happy looking dudes in that picture. Yeah, I think maybe at this upcoming Arthur conference, there will be some talk about Arthur packets, Arthur parameters in the like categorical Langlands case. Yeah, yeah. But definitely like yeah, because normally like the stuff that I do, we don't look at the whole stack of all Langlands parameters. So like I have no idea about how the like moduli space of all Arthur parameters sits in there, for example. Find it totally surprising that the rational distances problem is unsolved for the four corners of the unit square. Huh? That is surprising. But let's look at this first. Operator K theory sounds cool already. It suggests a link between the K theory of the reduced C star algebra of a group. Okay. And the K homology of the classifying space of proper actions of that group. Okay. So we've got some topological group. We've got the C star algebra on it, and the classifying space of proper actions. Interesting. Okay. The conjecture sets up a correspondence between different areas of mathematics. Sure. The conjecture, if true, would have some older famous conjectures as consequences. For instance, the surjectivity part implies some other conjecture. And the injectivity is related to Novikov. Okay. Also, index theory. M plays a part in non-commutative geometry. Well, not surprising given whose namesake is on the conjecture. Okay. So second countable locally compact group. One can define a morphism. Oh my god, what the hell is going on there? Called the assembly map from equivariant K homology. With gamma compact supports. I don't know what it means to be gamma compact. I don't know compact modulo gamma, maybe something like that. Of the classifying space of proper actions. Yeah, I still don't know what that is. Yeah, I mean, crazy. Understanding the statement of this conjecture seems like I need to do a little more reading. Oh my god. As the left-hand side tends to be more easily accessible than the right-hand side. Okay, whatever you say, Mr. Wikiman. Well, I mean, I guess it's not so crazy. I could imagine, right, classifying space of a group. I could imagine somehow this is supposed to be a classifying space of proper actions, right? So what does that mean? I guess this should sit over a space B gamma underline, and then every proper action can be obtained by like pulling back a map from there, and it's well defined up to homotopy. Oh, by the way, I want to thank you guys. I think some of you are here who pointed me towards Karubi's book, which I happened to have a hard copy of already, and I haven't been studying it in detail, but I was last night. I was reading it as some bedtime reading, and just flipping through some of the pages and looking at like the proofs of. Well, I do eventually want to better understand in detail the proof of the how you can describe every vector bundle on this on Sn by taking sort of like the two hemispheres, taking the trivial bundle on two hemispheres and just describing the clutching function on the intersection of the n-1 sphere. I thought that was really cool. And then, of course, yeah, the method of using the sort of method that he takes to prove the Serre-Swan theorem was really cool. I was reading about it. Yeah. Yeah, I haven't, definitely don't understand, didn't read all through his proof of blot periodicity yet, but yeah, probably I'll get there. Would be fun, I think, to someday go through that book in more detail, but alas, so many hours in the day. Okay, it's been resolved in all of these cases. Huh. It was a long-standing problem since the days of the conjecture to expose a single infinite property T group that satisfies it. However, such a group was given by Laforgue in 98. Wow. SL3QP. Maybe, should I do a comment if I should do SL4QP? Probably crazy. It's probably crazy stuff. Yeah. Okay. I think I'm gonna go soon. But let me say one thing I want to work towards. So we talked about this problem. Yeah. Vincent Laforgue is a guy who proved a lot of things. Including function field Langlands, yes. Yeah. Yeah, Caribbean envelope for the win, indeed, Boris. So here's something I want to think about. So we did in detail go through this example of C star acting on C, where T acts on Z by squaring, and we got those examples of D modules I've talked about a million times up above. But now here's an example I want to work out, and there's different versions of this I want to work out actually, but now I want to consider the following variety. So I'm going to look at all 2x2 matrices, and I'm going to have the group G acting on it is going to be hello Yaman. I'm going to have GL2 cross GL2. Acting on it. And how is it going to act? A pair of matrices will act on, well, I said X, but I don't know, maybe I'll act on an element of X, call it V, by going AX B inverse, sending X to AX B inverse. And so it turns out you can show that this variety will decompose into 3 orbits. So actually, how do I want to label this? 0, 1, and 2 being the ranks of these matrices. So there's 3 orbits. So this is just the 0, this is just the 0 matrix. This is all of the matrices of rank 1. So those would be all matrices which are not equal to the zero matrix, but have determinant 0. So xy minus, xw minus zy is equal to 0. And then C3 would be the rank 2 matrices. So XYZ, where the determinant is not equal to 0. Okay, and I already know in the back of my mind what the perverse sheaves should look like, but I've never worked out the D modules. So I kind of want to work out the D modules and the characteristic cycles. And I know from other methods what the characteristic cycles should look like. And so the orbits have, right, the closure of C naught is C naught. The closure of C1 is the union of C naught and C1. And the closure of C2, of course, is the entire space. And so what do we need to do to work out the D modules that we care about? Well, in this case, so this is a first case. There's sort of spicier versions of this, let's say, that have non-trivial sheaves showing up. But because this is a GLN case, I just want to deal with the trivial sheaves. So basically, for each one of these orbits, I want to consider the trivial local system. And now, what do I need to do? I want to produce the D modules on this variety associated to it, and compute their characteristic cycles. So maybe I'll try hashing through some of this live tomorrow, but that's going to do it for today. So go prove some stuff. Like I said, you guys gotta tell me about it. You gotta tell me what you proved. So tomorrow, come armed with proofs and questions.